Two fans can both be labeled 1000 CFM, yet only one may deliver the airflow your system needs. The reason is simple: CFM measures volume per minute, but it does not describe the resistance the fan must overcome. CFM means cubic feet per minute. Imagine 1 cubic foot parcel of air crossing this plane every second. 60 parcels cross in 1 minute, so the flow is 60 CFM. 1 CFM is about 1.7 cubic meters per hour. It is a rate of volume, not airspeed, pressure, cooling capacity, or fan quality. You can also connect volume flow to velocity. When area is in square feet and average velocity is in feet per minute, CFM equals area times velocity. 500 feet per minute through 2 square feet equals 1000 CFM. Push the same flow through only 1 square foot and velocity doubles. That can increase draft, pressure loss, and noise even though the CFM is unchanged. How much airflow do you need? Start with the physics of the application, not a fan diameter. For general room ventilation, air changes per hour can provide a starting point. Multiply room volume in cubic feet by the target ACH, then divide by 60. A room 20 feet by 25 feet by 10 feet contains 5,000 cubic feet. At 6 air changes per hour, the nominal flow is 500 CFM. Code, occupancy, contaminants, distribution, and exhaust balance can change the final requirement. For equipment cooling, start from heat load and the allowed air temperature rise. Near standard air conditions, a useful sensible heat estimate is CFM equals about 1.76 times watts divided by temperature rise in degrees Celsius. 1000 watts with a 10 degrees Celsius rise gives about 176 CFM as an ideal baseline. Altitude, recirculation, component hotspots, and system losses still have to be considered. Now comes the part that prevents most sizing mistakes. A catalog free air number is measured near zero external pressure. Add a filter, coil, grill, heat exchanger, or duct, and the system resistance rises approximately with airflow squared. The delivered CFM becomes the intersection of the fan curve and the system curve. That intersection, not the large number printed on a listing, is the operating point. This is why airflow testing is more than watching a fan spin. In a controlled tunnel, the fan is measured through a series of pressure conditions. Each measured flow and pressure pair becomes 1 point on the performance curve. The useful selection question is therefore not, what is the maximum CFM? It is, how many CFM will this fan deliver at my required static pressure? Air distribution matters too. A system may move the correct total CFM while starving one side of a coil or sending a high-velocity jet through another section. Free area, inlet clearance, bends, obstructions, leakage, and outlet geometry decide where the air actually goes. Total flow and local velocity must both be checked. Too little airflow can cause overheating, poor indoor air quality, low heat exchanger capacity, or inadequate capture. Too much can create drafts, noise, coil carryover, wasted power, and unstable control. The best target is not the biggest number. It is enough airflow, delivered uniformly, at the real operating point. Before selecting a fan, document the sizing method, target CFM or cubic meters per hour, required static pressure, air density and temperature, contamination, duty cycle, noise limit, available space, electrical supply, and control range. Then verify the complete tested curve, not one headline value. For an airflow and duty point review, visit longwellfans.com.